Hi all, welcome to module 9. In this module, we'll be talking about transactions and ACID properties. Our two objectives are to understand why transactions are needed and what ACID properties mean. So, we're going to look at two specific use cases to understand why transactions are needed. We're going to look at failures in the system that can cause inconsistency in our database, and we're also going to look at concurrency and how concurrency can cause a loss of isolation. Don't worry about what these mean because we'll be understanding that via examples over the course of this module. So first, let's try to understand that how failures can cause invalid states to exist in our database. Suppose we are reading data and writing data to a database, and suddenly there is a system failure, which could be a power failure or a disk failure or a software failure, and this causes our database to be in an invalid state. So just to take an example of an e-commerce kind of modeling, on the left we have a shopping cart, and the shopping cart contains 3 products, and this entire shopping cart has not been ordered, so we see that the is ordered flag is set to false. Once the entire order is placed and the payment is done, let's say we move to another state of our database where all the is ordered flags have turned to true, and in the order table 3 new rows have been created that say that the order has been placed for 3 of these products. Now, while both the state on the left and the state on the right are completely valid states, because of a system failure in the middle, maybe all of the items in the tables might not get updated, and we might end up with a state like this where not all the is ordered values are updated and all the new rows have not been created. So this is an invalid state, right? Ideally what we want is we want to be here or we want to be here. We never want to have a situation where we're in the middle. And if by chance there is a failure, then we should be able to roll back to the previous state, and then we should be able to restart the entire order process again. This process of undoing our operations is called rolling back. So this is one use case where we need this is an example of where we need some kind of atomicity to ensure that our database is in a valid state. And by atomicity, we mean that we should have an all or none kind of situation where either the entire set of operations happen or they don't happen at all. Let's look at another example, a slightly more complex example. Let's say we have a database which contains a table which contains a value, let's say which is a bank balance, right? So we have a 1,000 rupee bank balance to start with. Now, let's say somebody is going to update this bank balance. Let's say somebody is adding 1,000 rupees to our bank account. So user 1 is reading the value 1,000, is in adding the value plus 1,000 to it, and is writing the new value. So the new value 2,000 gets written. But while user 1 is reading and writing this new value, user 2 is also trying to add 1,000 rupees to this bank balance, and let's say 1,000 rupees is being read, 1,000 rupees was added and 2,000 rupees. User 2 thinks that the new balance is 2,000 rupees and tries to write this new balance of 2,000 rupees. So what is happening is that before the first write came through, the second user already read a value which was actually invalid, right? So we want to prevent this from happening while this is going on. And this business of desiring that user 1's actions are different from user 2's action is called isolation. So we want these operations to be in isolation from these operations. So this is another use case of why we need something special in the database to be able to handle these use cases. This is where database transactions come in. They provide, in a sense, an all or nothing kind of a feature, and they also provide this kind of an isolation that we need. For example, instead of issuing SQL statements one by one, we would issue an SQL statement called begin transaction, after which maybe we do a select operation, an insert operation, update operation, delete operation. We do a bunch of other SQL operations, and after finishing our SQL operations, we issue a last statement called end transaction. Now this entire sequence of steps is called a transaction. In case there is a system failure or something goes wrong, the database will ensure that that all of these operations are rolled back, and we see the database as it was before this begin transaction happened. So this is how we handle failures with transactions. Suppose multiple transactions are happening, right? Like in this case where user 1 has a transaction and user 2 has a transaction. If user 1's transactions and user 2's transactions cause a conflict by updating or referring to the same value, one of the transactions will be deliberately failed and will be rolled back so that we have an isolation effect between these two transactions. So as you can imagine, transactions are extremely valuable for financial or transactional applications. A lot of the times, modeling our data well, and especially normalizing our data models, can reduce the requirements for having transactions. Let's say, for example, we have a simple user and groups kind of modeling. So we have a user table and a groups table. Inside the user table, we store the user ID, the username, and the group that the user belongs to. Right? And in the group table, let's say that we store the group ID, the group name, and an array of users, say as a JSON column. So in this situation, if a membership is updated, let's say the group of a particular user is changed, not only do we have to update the user table and change the group ID, but we also have to go to the group table and update the users array. We have to do both of these operations transactionally. If we do one operation and the other operation does not go through, we'll have an inconsistent state and we won't know what the truth is. We won't know whether the group table has the true data or the user table has the true data. So modeling our data well and ensuring that this users array is not used and we're only using a group ID here, which has a foreign key constraint to the group table. This will ensure that we don't actually need to use a transaction and we can get away with a single SQL state. These properties of a transactions that we have talked about are actually called ACID properties. So let's understand what ACID stands for. Atomicity, which means that operations are all or nothing. Consistency means that the entire database, which means that if we have foreign key constraints or indexes, all the structures in the database move from one consistent state to another consistent state. Isolation refers to the property that while concurrent transactions are happening, they are perfectly equivalent to those transactions having executed in sequence one after another. Durability refers to the fact that transactions should actually be committed to disk so that if a transaction is marked as completed, it remains safe to the disk even if the database is restarted or if there's any kind of failure that causes the database to restart. So transactions that have ACID properties are very important to creating applications that are stable and need a very high amount of data integrity. The most important things to take away from this module are that transactions are very valuable DBMS features, especially for certain kinds of applications. It is important to understand that transactions don't have to be provided by the database. We can create transactions in the application as well, but we would have to write much more complicated application logic to ensure that while a particular transaction is happening, no other transactions are allowed. We would have to write application logic to ensure that in case there is a failure, we're able to recover from those failures so that operations can be rolled back, and we would essentially have to do all of the work that a DBMS is doing for us in our application code. The price that we pay for transactions is that it can slow overall operations down because the database cannot do multiple operations perfectly concurrently. We also understood that doing good data modeling can prevent the excessive use of transactions, and we know that a transaction to have a high degree of data integrity must support all four ACID properties.